This is our last set of topics. We'll be talking about fluids. So this does kind of feel like it comes out of nowhere since we've been talking about modern physics, but it is a nice way of reviewing some mechanics concepts way back from 121, and it covers up some gaps that we had in the course. So we're going to be talking about some basic fluid properties to start, some static fluids equations, things like buoyancy, and then two dynamic fluid equations and moving fluids in terms of pressure, velocity, and height. So when we're talking about fluids, right, we're talking about liquids or gases. We're thinking probably in terms of some quantities that we haven't thought about in a physics class so much, things like volume, right? So we can think about volume in meters cubed, but we might also want to think about volume in terms of liters, the connection being like a cubic centimeter is 1 milliliter. And right, a cubic meter is not 100 cubic centimeters, it's 100 centimeters quantity cubed. So it's like 10 to the 6 cubic centimeters. And if I think about a liter, that's 1,000 milliliters or 1,000 cubic centimeters. We might be thinking about pressure, which would be in terms of pascals, so like a Newton per meter squared. And that's something we think about as like a force per unit area. That means if I want to find the force exerted by a fluid on the walls of its container, in general, I'm going to be integrating the pressure over the area. When we're talking about pressure, right, there is some air pressure around us all the time. So we might be talking about like a gauge pressure, which would be the absolute pressure subtracting the atmospheric pressure surrounding us, which can be in units, helpful units like 1 atmosphere, also 101.3 kilopascals. Density, right? Density is an important quantity we think about in terms of a fluid. Our standard for density is water, which would be a kilogram per liter. If I'm talking about air, it gets a little bit fuzzy, right? Air is compressible, so it can have different densities at sea level. Standard temperature and pressure, the density of air that we use is 1.2 kilograms per cubic meter. So one of the equations that we've seen in the book is that the pressure for a fluid is going to increase depending on depth. So if I think about depth in a body of water, the very top surface of the water is at the same pressure as the air. And I can see that by looking at a point on the surface of the water and identifying that it doesn't accelerate up or down. So as I get deeper, right, I can imagine the weight of the water on top pushing down. And so I can think about the pressure increasing, and the function I get looks like air pressure plus density times g times depth. Okay, so one of the multiple choice questions for this week was just asking about what quantity is going to be conserved if I have something like a liter of gasoline evaporating, and we think about mass, right? So we can calculate the amount of mass in terms of, right, density times volume. So that's going to be 0.77 kilograms, right? And then when it evaporates, it takes up a larger volume. And so the new density, right, the final density of the evaporated gasoline, I could write in terms of that same amount of mass divided by the new volume. So that gives us a mass of 50 grams per liter for the evaporated gasoline. All right, so one of these questions that we worked on at home was basically an elaborate Futurama reference, if anyone remembers that show. The joke here is that I can imagine that something like a spacecraft is sealed, right, to keep all the air in, and so how is it really different from a submarine? And then we can ask the question, okay, how is the pressure that this object is exposed to different in space versus on the surface of the Earth versus underwater? So on the surface of Earth, we can imagine that there's atmospheric pressure inside the vessel and outside, and so there's a net pressure on a point on the spacecraft of 0. If I'm in space, there's no external pressure or very little, so I can imagine a net pressure of 1 atmosphere outwards. If I'm underwater, then there's air pressure pushing outwards, and water or pressure pushing inwards depending on depth. And so the net pressure goes like the density of the water times G times depth. Quite quickly, that number gets pretty big. If I'm up at 100 meters deep, then I'm looking at 1,000 kilopascals of net pressure, or around 10 atmospheres. And if I'm at 1,000 meters deep, then I'm looking at more like 100 atmospheres. So the spacecraft, right, being designed to take between 0 and 1 for the most part, is not going to survive at large depths for very long. For the second part of this, if I want to find the net force on the walls, if I model the ship as a cylinder, I want to really just break this up into like the top of the cylinder, the bottom of the cylinder, and the sides. And technically, I should keep track of the pressure varying in terms of depth. So on the top surface, it's relatively easy to find the net force on the ship, as I can take the water pressure times the pi r squared, the radius, the area of the top surface. For the bottom, the pressure is technically going to be a bit bigger, right? Because the bottom of the spacecraft is a little bit deeper in the water, and so subject to a higher pressure. And here at the sides, right, technically I really should be integrating. Can integrate 2 pi r to make it around the circumference of the circle, and then integrate dh to make it to the bottom of the cylinder. And as I integrate, right, the pressure is changing, which is why I want to integrate this and not just treat it as a product of pressure times area. Okay, this is one that we had a little bit of challenge with. It's kind of a really good problem because it seems really straightforward, but it forces us to really cope with a lot of nuance in terms of what's happening in terms of buoyancy. So we were finding the buoyant force on a perfectly cube helium balloon. Obviously, we've all gone to a party store and bought a balloon that was a perfect cube. Why not? And the trick to this problem is really free body diagrams, right? We really have to remember to draw free body diagrams and how to draw free body diagrams. The upward force would be the buoyant force, which we can interpret as the density of the displaced air, or sorry, the weight of the displaced air. The downward forces could correspond to the tension on the string, the weight of the helium inside the balloon, and the weight of the fabric of the balloon itself. So the volume of the balloon, we can take 30 centimeters and cube it. The buoyant force then looks like the weight of the air displaced. So that's going to be the density of the air times G times the volume. So that corresponds to the weight of the displaced air. And then I can say, okay, the net force should be 0. And so the buoyant force should be canceled out by the sum of all of these downward forces. I'm looking for tension here, right? I'm looking to how hard I have to pull down on the string to keep the balloon from floating away. And so if I put in for everything else in this equation, the remaining tension looks like 0.192 newtons. So a cool problem, right? Buoyancy being a simple but interesting concept with some nuance to it. Okay, so this would be an example of a problem where the object was entirely submersed in a fluid and I was finding the buoyancy. If the object is partially submersed, it's really the same sort of problem, but there's some differences in terms of nuance and what would the easiest way to solve it be. So if I imagine that a wooden block is floating in water with a certain fraction of its height below the surface, right, I can imagine the buoyant force now still as being the volume of fluid displaced, but that just means now I'm taking the density of water times G times the submerged volume. So times this area times 1/3 of the height. So that buoyant force then corresponds to just the weight of the displaced fluid. And so if I want to, let's see. If I want to figure out how much weight, or sorry, the density of the wood, right, I could figure out that this buoyant force has to be canceling out the entire weight of the block of wood. So that is going to be the density times the volume of the whole block, right? Because the whole block experiences the weight force, while only the submerged volume affects the buoyant force. And so from here, I can get rearrange my equation algebraically and get an expression for the density of water compared to the density of wood. And I get that wood is 1/3 of the density of water. Okay, the next part was imagining stacking, how much weight I could stack on the top. And so if I visualize what happens when I stack weight on this block, right, as I stack some weight here, the upward force needs to be larger, and so more of the block would be under the water. The limiting case here would be I stack so much weight that nearly the whole block is under the water. So that would be my maximum buoyant force could be thought of as the density of water times the volume of the entire block times g. And so the maximum weight I could put on would be equal to the maximum buoyant force and corresponds to the weight of the block, which we found earlier, plus the weight of whatever stuff I want to pile on top. And so if the maximum buoyant force looks like 2,000 kilograms times g, then that means I can pile on another 1,333 kilograms worth of stuff on here before the block sinks. Okay, so thinking more about what happens with buoyancy, if I imagine I have a cube of iron that sinks, how deep does it go before it stops sinking? And this is kind of an interesting concept question because we might think that, you know, the pressure here is getting larger as the object gets deeper, right? It's the air pressure plus density times g times depth. So that pressure is getting bigger as the block sinks. We might imagine eventually that will be large enough to hold the block up, but that's not quite right because we also have to imagine, right, there's a downward pressure that's also getting larger that corresponds to, right, the depth of the top of the object. And so the difference in pressure is going to actually stay the same. And so the net buoyant force is going to, always going to stay the same here. The weight of the displaced fluid is always the same. And so what I can imagine is this is like the pressure in the bottom, this is the pressure at the top. Subtract the pressure at the top from the pressure at the bottom, multiply times area, and I'm going to get density times g times height times area, right? Or the density of the water times g times the volume of the object. So that's not dependent on depth at all. So in fact, the buoyant force stays constant as depth increases. And so this object is going to sink all the way to the bottom. Another concept question about buoyancy, if I have an aluminum block and a brass block and they both sink, if they are the same size and shape, then they must have the same volume, which means they both displace the same amount of volume. And if they're displacing a same amount of volume, then they must displace the same amount of mass, right? And we interpret the buoyant force as the weight of the water being displaced. So that should be the same as well. So then what's different between these two objects if they have different densities? Well, they have different densities, they're going to have different weights. And so while they have the same buoyant force, they're going to have different weight forces. And so they're going to sink at different weights. So they're going to accelerate different amounts based on their different densities. But since they both sink and they're both the same volume, they're both displacing the same amount of water and therefore experiencing the same buoyant force. Okay, so that's enough talking about buoyancy. Let's talk a little bit about pressure. So the example that I came up with is related to hydraulic systems, right? Specifically, right, in cars. For most vehicles, when you step on a brake pedal, you're compressing, maybe indirectly, a cylinder of fluid. And so the idea is you want some mechanical advantage. So when you push on the brake pedal, that force gets multiplied to be pushed onto the brake disc. And this is typically done with hydraulics. So if I imagine pushing with a force of 20 newtons to a small piston, then I'm adding pressure to this fluid. And if I have a sealed system, then that same pressure is going to be exerted on the larger cylinder. So if I keep the pressure inside the system constant, then the force on the pedal divided by the area of the pedal will be equal to the force on the brake disc divided by the area of the brake cylinder. I can also use the idea that the amount of volume of fluid being moved is the area times the length. So the way I can really interpret this is, right, if I am pushing on a small cylinder, the larger cylinder is going to experience way more force, right? So I get 500 newtons is the force on the large cylinder. And the reason that doesn't mess up conservation of energy is related to the difference in the change of the length moved by the pedal cylinder and the brake cylinder. So because those delta L's are different, even though the forces are different, the work done at the pedal and the work done on the brake disc are the same. So the brake disc only is going to move by a few millimeters to act on the brakes. Meanwhile, your pedal moves several centimeters. So that multiplication of force comes with a decrease in distance to keep the work done the same. So you're putting the same amount of energy into the system, but you're delivering a larger force. And that's how we get a mechanical advantage with hydraulics. Okay, so now we're going to kind of segue into dynamic fluid equations, specifically the continuity equation first. So the idea of the continuity equation is that from one side of a system to the other, mass isn't going anywhere. So if we have a certain amount of mass entering a pipe, the same amount of mass has to come out of the pipe because it can't kind of stack up anywhere. It can't be created or be destroyed. If I have an incompressible fluid, like water and most fluids, then the density is the same as well. So we can write the continuity equation in terms of this volume flow rate. So volume in, which we commonly write as Q, is equal to volume out. And the idea of a volume flow rate is I'm taking the velocity times the area. So I'm getting a flow rate that looks like potentially like cubic meters per second of water, or whichever fluid is moving. The second equation that we're going to use for dynamic fluids is Bernoulli's equation. So for a static fluid, right, we talked about how the pressure is changing with depth. The idea here is that if I have a dynamic fluid, then I have the same sort of situation, but now I'm also thinking about the fluid potentially moving. So now I'm starting to think in terms of the energy in a small piece of fluid here. So if I imagine that there's a certain difference in pressure, for example, that difference in pressure could accelerate water. And so I'd have a different amount of energy per unit water. So I can think about pressure as like the work done per little piece of water. I can think about the rho times g times height as kind of like the potential energy for a little unit of water. And I can think about 1/2 times the density times v squared as the kinetic energy of a little bit of water. And so this is basically telling me that if I'm changing energy, there has to be a difference in pressure to correspond to work being done on a small piece of water. Okay, so in terms of our quantitative practice, the first was related to a syringe, where I imagine I am pushing on a syringe that has a certain diameter plunger and squeezing fluid through a much smaller diameter. This is basically a continuity equation problem. So I can take the flow rate in and set it equal to the flow rate coming out. So the flow rate in is going to be the area times the linear velocity, likewise coming out. And so the linear velocity corresponds to how far the plunger has moved in how much time. So I can say that's 10 seconds over time. The velocity coming out, right, is going to be, or the area is going to be pi times the radius of the plunger squared. And same thing for the fluid coming out. So I can find the velocity coming out in terms of, the velocity coming in is the velocity coming out times the area coming out divided by the area coming in. That gives me 2 centimeters per second is the velocity coming in. And then I can take the time as the distance covered divided by that velocity. So it takes 5 seconds to completely push the plunger into this syringe. Okay, so let's look at some kind of conceptual question about Bernoulli here. So I'm going to look at 3 nozzles, a wide nozzle, a medium, and a small one, and ask about their velocity and pressure. So if they all have the same velocity coming in, then examining the velocity coming out is just looking at the continuity equation. So the narrowest, right, if they have the same Q in, corresponds to V in times area in, equals to the, or is equal to the velocity going out times the area going out. So this has the smallest area on the output side, and so it must have the largest velocity coming out. So nozzle 3 has the highest output velocity. So then we have to look at what's going on with pressure. So if I look at what's going on with pressure, right, this is where Bernoulli's equation comes in. So the pressure plus rho times v squared over 2 has to be constant in the case where I have no change in height. So then I could represent the change in pressure as the change in this rho v squared over 2. Or in other words, if I'm going to speed up the fluid by a lot, then the pressure has to decrease by a lot. So I have a big pressure coming in and a small pressure coming out. And that large difference in pressure provides a net force on the fluid here, thus having a large amount of work being done on that fluid, which leads us to the larger change in velocity. So up here for the widest, right, the velocity doesn't change by that much. So the pressure drop is also going to be a little bit smaller. So in this case, actually, nozzle 1 has the highest output pressure, where nozzle 3 has the largest velocity. And so the difference in pressure we can link to the change in velocity with Bernoulli. Okay, so then let's look at some quantitative ways of using Bernoulli. So one example is kind of thinking about like a water tower, or if I have a large container of water and the water's at a certain height inside the bucket, then I make a small hole in the bucket. What is the pressure at the opening and velocity? And how is that different if I just let water flow straight out of the bucket or if I plug the hole with my finger? So the idea behind using Bernoulli's equation in any quantitative problem is calculating this expression at different points, right? We know that this pressure plus rho gh plus 1/2 rho v squared is constant, but we don't know what it's equal to. So what we do is we find it at 3 points and set those, or at several points and set those expressions equal to one another. So for me, the most interesting points are probably the top of the bucket of water, the point at the height of the hole, and a point directly outside of the hole. So if I find pressure at each of those points plus 1/2 rho v squared plus rho gh, right, then I can set those 3 expressions equal to one another. Up here at point 3, right, it's a fairly safe assumption that the velocity here is approximately 0. Right, if the hole is small, the water level is not dropping very fast. So I can say that Bernoulli's expression here is roughly the atmospheric pressure plus rho times g times height. And to make things easy for myself, I can set the height equals 0 to be wherever I want, just like I did with any other potential energy problem back in 121. So the height then I can just write as 3.9 meters. over here, right, for point 1, again, I can assume I might not be thinking that the velocity of the water is too high there, but I'll leave that term in for now. I have a pressure that is definitely not atmospheric pressure. And then out here at point 2, this point is out in the atmosphere. And so I do actually have atmospheric pressure. And then I've got to figure out what's going on with the velocity. So I am a little suspicious that this velocity here is probably 0, while this velocity here is the one that I'm looking for. So at point 1, right, I can find the pressure there is going to be equal to whatever this constant is. I can find the constant from any of the other 2 expressions. So for example, I can say atmospheric pressure plus rho times g times height, right? Whatever I find for that, that's going to be equal to the pressure at point 1. I don't actually need to find the pressure at point 1 to do this problem, but it's important to note that it's there and it's some positive number bigger than P naught. I can also set this expression equal to the Bernoulli expression over at point 2, right? Then it becomes equal to the atmospheric pressure plus this pseudokinetic energy term. If I solve for velocity in that term, and I get 8.8 meters per second. You've noticed, right, we've set the pressure here at point 2 to be equal to the atmospheric pressure. So what we have here, just like with the hose problem, is we have a bigger pressure over here, and then just atmospheric pressure on the outside of the bucket. And just like with the nozzle, it's that difference in pressure that's going to act to speed up the water. So the fact that there's a velocity of water coming out of the bucket while water inside the bucket is relatively stationary comes down to the work being done by that difference in pressure at the hole. If I were to put my finger in that hole, right, then all of a sudden there would be no velocity, there'd be no pressure difference, and then I'd basically just be finding this pressure here at point 1. So I can find that just by taking atmospheric pressure plus rho times g times the height of the top, right? Find the height of this point up here and use that to calculate the pressure. Or I could just do density times g times depth if I wanted to do it that way. Okay, so the second Bernoulli equation practice is going to require us to use continuity equation and Bernoulli's equation at the same time. So we have a pump attached to a pipe. The pump itself is below ground and the water emerges from a fountain at ground level with a certain velocity. So in this case, the 2 points I'm really interested in are the point where the water leaves the fountain and the point where the water leaves the pump. So to write down Bernoulli's equation, I'm going to write down my expression in terms of P plus rho V squared plus rho GH, and I'm going to write it down in 2 spots. And because it's constant, I'm going to set those 2 expressions equal to one another. So at the pump, I have whatever pressure the water's coming out of the pump with, plus 1/2 times the density of water times the velocity it's coming out of the pump with, or into the pipe, if you like. And that's going to be equal to the pressure up here, right? Since this is emerging into air, this is just going to be an atmospheric pressure. 1/2 rho times the velocity squared, velocity being given in the problem, and then rho times g times height. So I'm going to set h equals 0 to the height of the pump. And so the water coming out of the fountain has some extra potential energy relative to the water coming in. You notice we still don't quite have enough information here because we've got 2 unknowns on the left side of the problem. So we do actually need to also use the continuity equation here. So to use the continuity equation, I'm going to say that, right, Q in is equal to Q out. And so the velocity coming in times the area coming in is equal to the velocity out times the area out. And so I can find the velocity, right, leaving the pump or coming into the pipe at the ratio of the areas times the 20 meters per second. And so that's going to end up being 0.8 meters per second. So now that I've got the velocity coming in, then I can go back to Bernoulli's equation. And now I only have one unknown, which is that pressure. So now I can rearrange to get either P minus P naught or just P. and which one I go for tells me whether I'm looking for gauge pressure or absolute pressure. And then my answer depends also on whether I'm looking for gauge pressure or absolute pressure. So if I just solve for P, I get 315.7 kilopascals. If I subtract P naught, that gives me gauge pressure, which is 214.4 kilopascals. And if I ask for pressure on a problem, I'll specify which one I want. Or if it's a free answer problem, you can just tell me which one you're giving me and it'll be fine. Okay, so that's everything we need to talk about in terms of fluids. Let me know if you have any further questions, and hope you had a good quarter up to this point. Not much left past here other than a few more assignments and the final.